Year 13 Pure Maths revision video number 5. This will cover 4 questions on differentiation, integration and trigonometry. There are 2 questions involving integration. So, the first example, we've got to find the equation of the normal to this curve at a particular point. So we have the equation of the curve. We're going to differentiate it to find dy by dx. So 4x cubed minus 6x. And we're going to input the x value of 1 to find out the gradient of the tangent at this point. So that will give us a tangent with a gradient of negative 2, which means that the normal gradient, the perpendicular gradient, will equal 1/2. So the equation of the normal, y minus y1 equals m bracket x minus x1. We can say that y is equal to 1/2 x minus 1, or y equals 1/2 x minus 1/2. So for part 2, we've been given a similar curve, but this time the y-intercept is c rather than 2 as in part 1. And L is again the normal at the point where x equals 1. So when you differentiate this function here, you're going to get exactly the same derivative that we got last time, because of course this c will differentiate to give us 0. So this will have the same gradient function, which means that x equals 1, dy by dx will still equal negative 2, and the normal gradient will still equal 1/2, so that hasn't changed. Now what has changed is the y-coordinate at x equals 1. Previously, the y-coordinate at x equals 1 was equal to 0. And you can see that if you substitute in x equals 1 into this equation, you get 1 minus 3 plus 2, which is of course 0. So now the y-coordinate will be y equals 1 to the power of 4 minus 3 times 1 squared plus c. So that gives us c minus 2. Which means the equation of this straight line, of this normal, is y minus y1, which is y minus c take 2, equals m, 1/2, x minus x1, which is x take away 1. So we want to know the value of c for which this normal passes through the origin, which means that when x equals 0, y must equal 0, and we'll substitute that information into our equation for our normal. So that's 0 minus c plus 2 equals 1/2, and of course 0 minus 1 is just minus 1. And we then just need to simplify this, rearrange it, and find our value of c, which is c equals 2.5, or 5/2. So on to our next question, which is an integration question. We've got to find the area, total area of the shaded regions. Now, of course, this region falls under the x-axis, so it will be negative. So we are going to integrate this function here, which I'm going to expand as well. So it's x to the 4 minus 3x cubed. We're going to integrate this with respect to x. I'm not going to integrate it within limits for the moment. I'm going to do a general integration, or an indefinite integration as it's also called. So we get x to the power of 5 over 5 minus 3x to the power of 4 over 4, and of course there is a plus c as well, but that doesn't really matter because we're going to evaluate this in between limits. First of all, we're going to find area A, and area A is going to equal the result of my integration, evaluated between a lower limit of minus 1 and an upper limit of 0. Now the upper limit of 0 is obviously going to give us 0. My lower limit is going to give me negative 1/5 minus 3/4. This then gives me an answer of 19/20. So we now need to find this second shaded region here, and in order to do that, we need to evaluate the result of our integral here between 0 and this point here. Now, at point P, let's call it P, we know the y-coordinate is equal to 0. So if we set the equation of the curve equal to 0, we get x equals 0, which of course is the origin, but we also get x equals 3. So at P, we are dealing with point 3. So we need to evaluate x to the 5 over 5 minus 3x to the 4 over 4 between a lower limit of 0 and an upper limit of 3. Now the lower limit of 0 will just give us a 0, so we don't need to worry about that in a minute, but we do need to work out what we get from the upper limit being substituted in, and we get an overall answer of negative 243 over 20. So if we're working out the total area, we of course want to take 19 over 20 and add it to positive 243 over 20, which gives us an answer for the total area of the shaded regions together combined as 131 over 10 square units. So on to our second integration question. It's an integration by substitution. We've been given that information, and we're told that x equals e to the u. So differentiating dx by du equals e to the u. So dx is equal to e to the u du. So let's approach this integral. Now, in the integral we have ln of x. Now, we know that x is equal to e to the u, which means ln of x must be equal to u. So I can substitute in for ln of x all squared as u squared. And then dx, I can see it over here, is e to the u du. And I now have the integral of u squared e to the u, all with respect to u. So the whole integral is in terms of u. Now, this has got to be done as an integration by parts, and I've got to pick one part which has to be differentiated and one part which has to be integrated. Now, the tricky thing here is that the letter u is what we normally use when we set up our integration by parts, when we do the uv minus the integral of v du by dx, and that's now been used in another context. So to simplify this, there are lots of ways in which we might simplify this. I am going to set up my integration by parts formula, which normally has the form this format. But instead of u, because that's already within the body of this integral, we're going to replace u with t, just for simplicity. So t is going to equal u squared, because when we differentiate that, dt by du becomes 2u, and then dv by dx will actually have to be written as dv by du, and that will be e to the u. So v equals e to the u. So it is just the normal integration by parts, but the letter choice here might make this a little bit confusing, so be very careful with how you proceed. So let's start with our integration by parts. Now the first thing is the product of t and v. So that of course is u squared e to the u. Then we subtract from that the integral of v times dt by du. So that's going to be 2u e to the u du. And this now requires another round of integration by parts over here. So this is going to be our t, and this is going to be dv by du. So t is equal to 2u, dt by du will be 2, dv by du is going to equal e to the u, and v will equal e to the u. So let's start our integration by parts again. So eu squared e to the u stays the same. We now then apply our integration by parts again. So I'm going to put in a large square pair of brackets. So effectively we're on this part of the integration by parts here, the uv part, except in this case it's going to be t times v. So it's these two multiplied together. So that's 2u e to the u, take away the integral of, and now we're on to this part here. So that means we need the product of these two. That's still got to be integrated, so there's still work to be done here. So this is u squared e to the u minus 2u e to the u, and then minus minus will give me a plus, and then integrating this will still just give me 2e to the u plus c. Now, finishing this off, I have to substitute back in, so I replace anything that's in terms of u back in terms of x. So if you recall, u is equal to ln of x, so this is ln of x, e to the u is just x, minus 2 ln of x, x plus 2x plus c. And I think just for tidiness sake, I'm going to write this as x bracket ln x squared minus 2x ln x plus 2x plus a constant. So our last question involves some trigonometry. We have a shape consisting of an isosceles triangle ABC and a semicircle with AC as a diameter, and angle ABC is pi by 6 radians, and AB and BC are both 10 centimetres. Part 1, calculate the area of the shape. So of course the area is going to equal the area of this triangle, add the area of the semicircle. So the area of the triangle ABC is equal to a half times 10 times 10 times sine pi by 6, which comes to an answer of 25 centimetres squared. Now, to get the semicircle area, we need to know the radius, or at least the diameter. So we're going to work out the length here. Now, I'm going to actually do this by splitting this into a right angle triangle. I'm going to call this M here. AM is basically the radius of the circle. So we know that sine of half of that angle, so sine of pi by 12 is equal to the radius over 10. So this then gives me the radius equals 10 sine pi by 12. And then the area of the semicircle is equal to pi times r squared over 2, which gives me 10.522 dot dot. So the total area is of course the sum of these two values, which is 35.52 dot dot dot, or 35.5 centimetres squared to 3SF. Now, figure 6.2 shows a sector DEF of a circle radius 10 centimetres, angle DEF equals theta radians. The shapes in figures 6.1 and 6.2 have the same area. Find theta, giving your answer correct to 3SF. Now, for part 2, we know that the area of a sector is given in radians by the formula a half r squared theta, and this must be equal to 35.522 dot dot dot. Now, r we know is equal to the radius of the sector, which is 10. Theta is what we are looking for, so we simply do a little bit of rearrangement here to work out the value of theta. And this comes to 0.71044 dot dot dot, so 0.710 radians to 3 significant figures.